GLP-1 agonists like semaglutide suppress appetite by enhancing your brain and stomach satiety signals through multiple systems. GLP-1 is a natural hormone your body makes in response to nutrient intake. Understanding how these drugs work means understanding your own appetite control system. Here is what happens when GLP-1 activity increases. Part 1 through 3. The first system is in your brain, specifically a region called the hypothalamus. The hypothalamus integrates hunger and satiety signals to control eating behavior. GLP-1 receptors are distributed throughout the hypothalamus. In a zone called the arcuate nucleus, GLP-1 binds to these receptors and activates signaling pathways. This activates neurons called POMC cells, which release satiety-promoting neuropeptides. At the same time, GLP-1 inhibits hunger-promoting NPY and AGRP neurons. The brain also perceives satiety despite possible gastric emptiness. GLP-1 also works deeper in the brainstem, in regions that detect circulating hormone signals. One spot, called the area postrema, detects blood hormone levels. Another, called the nucleus tractus solitarius, integrates gut signals to higher brain regions. When GLP-1 hits both of these, satiety signaling enhances in multiple brain regions. Your brain perceives satiety despite possible gastric emptiness. If one signal system weakens, the others remain active, which reduces override risk via redundancy. Interestingly, GLP-1 agonists modulate dopamine reward without eliminating it, so food still sounds rewarding. You just do not want to eat very much of it. This creates a disconnect between desire and hunger. Your brain uses satiety as a stop signal without food intake, but enhancing brain signaling is only part of what makes these drugs work so well, which brings us to the stomach. The stomach is a key site of GLP-1 action. When you eat, your stomach actively processes and releases food. It releases food into the small intestine in a process called gastric emptying. While the stomach is distended, stretch receptors activate satiety pathways. GLP-1 agonists slow gastric emptying. The food stays in the stomach longer, so the stomach stays distended longer. That means the stretch receptors stay active, and satiety signals persist via vagus nerve to your brain for hours. GLP-1 agonists demonstrably delay gastric emptying in trials. Food takes measurably longer to leave the stomach. The vagus nerve transmits satiety signals via two appetite centers. This delay happens in addition to the brain signals, so the body receives satiety signals from two separate pathways. Because the stomach empties slower, fullness persists beyond typical hunger duration. Prolonged distension occurs without typical hunger response. Slower emptying means nutrients reach the small intestine more gradually. Steady nutrient absorption reduces post-meal blood sugar fluctuations and associated hunger. Gastric emptying delay modulates downstream hunger triggers via slowed absorption. Slow emptying, prolonged distension, and steady blood sugar work as integrated physiological mechanisms. The stomach is one component of multi-system satiety. Your gut continues hormonal signaling. Your gut produces hormones beyond GLP-1 that collectively regulate appetite. Ghrelin, leptin, and satiety peptides are key regulators. Ghrelin promotes hunger when elevated. Ghrelin levels fluctuate based on feeding state and meal timing. Ghrelin signals hunger to brain via circulation. GLP-1 agonists modestly reduce ghrelin levels. With less ghrelin, your brain receives fewer hunger signals. There is also leptin, which is the counterpart hormone. Leptin signals that energy stores are adequate and feeding should cease. In obesity, people often develop leptin resistance. Evidence suggests improvement in leptin sensitivity with GLP-1 agonists in some obese individuals. GLP-1 agonists reduce hunger signals and enhance stop signals. Other satiety hormones also regulate appetite. Cholecystokinin, or CCK, releases from the intestines when food enters. CCK signals satiety and slows gastric emptying. Peptide YY, or PYY, releases in response to nutrients and signals fullness. GLP-1 agonists enhance or work alongside these hormones, amplifying satiety signaling. These hormones signal via the vagus nerve to appetite control centers. They also travel through the bloodstream to reach appetite control centers throughout the central nervous system. If one hormone signal weakens, others remain active. Your gut systems regulate eating, and when you increase GLP-1, multiple pathways engage. Reduce ghrelin, improved leptin signaling, enhanced CCK and PYY signals work together. Appetite suppression shows redundancy via multiple mechanisms rather than dependence on one alone. GLP-1 agonists work through three parallel pathways. Channel 1 enhances brain satiety signals via hypothalamus and brainstem. Channel 2 prolongs stomach distension and fullness signaling. Channel 3 modulates hormones towards satiety. All three occur simultaneously. Multiple systems coordinate hunger signaling and all work toward appetite reduction. Redundancy becomes elegant design, making appetite suppression highly resistant to override. The relative strength of each mechanism varies from person to person, which is why some people see stronger effects than others. The body may develop reduced effect over time, currently under investigation. Many people on these drugs experience appetite decrease, particularly in early treatment, though responses vary. Hunger reduction occurs more than fullness sensation arriving. Your appetite system reflects evolution for scarcity, creating an unusual pattern when satiety signals without food intake. Appetite suppression differs from food tasting bad. Many people report food still sounds appealing, yet they do not want much of it. The distinction between reward and hunger signals means people can crave food but consume smaller portions. Multiple systems working together suggest that single lifestyle changes may not fully counteract appetite suppression, which is why the drug can work when people are not actively restricting eating. Research from NIH and peer-reviewed journals supports these documented mechanisms. Animal studies show GLP-1 receptors activating POMC neurons in brain regions. Gastric emptying delay is documented in controlled trials. Ghrelin modulation, leptin signaling changes, and PYY effects appear in published research. Appetite suppression is observed across many people. Higher GLP-1 agonist doses show dose-dependent effects in some cases. Animal models without GLP-1 receptors show minimal appetite suppression, supporting the role of GLP-1 signaling. Appetite suppression onset varies across individuals and formulations. The mechanisms are well studied in animal models and supported by human clinical data. Your body produces GLP-1. Your intestinal cells produce GLP-1 in response to nutrient intake. Natural GLP-1 levels are typically modest. These drugs increase GLP-1 signaling in your appetite system. GLP-1 agonists modulate endogenous GLP-1 pathways to enhance satiety. This video is educational and explains proposed mechanical pathways of these drugs. Consult a doctor about whether GLP-1 agonists are appropriate for you and how to manage any changes when stopping. Now that you know how GLP-1 reduces hunger signals, the next question is what happens to your body after discontinuation, and that is where post-treatment appetite changes require medical guidance.